Typhoon Fung Wong just struck the Philippines with 185 km/h winds, and scientists are terrified by what they found because this monster storm is breaking every rule in the meteorological playbook. Picture a typhoon so massive it covers 2/3 of an entire country, packing winds of 230 km/h that triggered the Philippines' highest possible warning level. Signal number 5, reserved for catastrophic destruction. Over 1 million people have been evacuated as this beast made landfall in Aurora province, already claiming 2 lives and turning entire regions into disaster zones. But here's what has weather experts completely stunned. Fung Wong's wind and rain bands are impossibly wide, stretching across distances that should be physically impossible for a single storm system. Satellite imagery shows a perfectly organized eye wall that is maintaining its structure despite hitting mountainous terrain that should tear any normal typhoon apart. Even more bizarre, the storm is generating storm surge and flooding patterns that do not match its official category. As if it is drawing power from sources meteorologists cannot identify, emergency teams are bracing for impacts that exceed their worst-case scenarios. Is Fung Wong just an unusually large typhoon? Or are we witnessing the evolution of a new class of superstorm that could redefine what we think tropical cyclones can do? Every year, the Philippines braces for a relentless parade of storms. On average, between 20 and 25 tropical cyclones enter or form in the Philippine area of responsibility each year. About half of those make landfall, bringing a regular cycle of disruption, loss, and rebuilding. In recent decades, the country has seen a marked increase in the number of so-called super typhoons, storms with sustained winds exceeding 185 km/h. This new reality has pushed entire communities to live with an ever-present sense of risk, especially in Luzon and the Visayas, where the brunt of these tempests is often felt. The past 20 years have rewritten the baseline for what is considered a dangerous storm. Typhoons that once seemed rare now strike almost every season. Government agencies and local leaders have been forced to adapt, refining evacuation plans and investing in early warning systems. Forecasting has become a race as storms grow stronger and more unpredictable. Meteorologists rely on a network of satellites, Doppler radars, and automated weather stations to track these systems as they form and intensify over the warm Pacific waters. This is the environment into which Typhoon Fung Wong arrived, not as an isolated monster, but as the latest and most extreme entry in a long, accelerating series of storms. For the people of the Philippines, the threat is never abstract. It is woven into daily life, shaping everything from school calendars to the design of homes. Each storm tests the limits of preparation, and each year those limits are pushed a little further. Meteorologists in the Philippines depend on a web of sensors and cross-checks to keep the country one step ahead of disaster. Every tropical cyclone is tracked by a combination of land-based weather stations, Doppler radar, satellites, and coastal buoys. Each system provides a different piece of the puzzle: surface winds, rainfall, pressure, and the shifting shape of the storm itself. PAGASA, the National Weather Service, has strict protocols. No single reading is ever trusted alone. Satellite images are compared with radar scans, and both are checked against the real-time numbers coming in from ground stations. If one sensor goes down, another is supposed to fill the gap. Redundancy is not just best practice. It is the only way to catch sudden changes that could mean the difference between a safe evacuation and a tragedy. Analysts work in 30-minute windows, layering new data over the last, hunting for discrepancies. If two sources disagree by more than a few percent, the team pauses to investigate before issuing an alert. For a major upgrade like raising the wind signal to the highest level, confirmation from at least 2 independent sensor types is required. Manual review by senior forecasters is mandatory when the network is degraded or readings seem off. This rigorous multi-layered approach was stress-tested just days before Fung Wong, when Typhoon Kao Magi battered Luzon and knocked out several key stations. The strain left gaps that would haunt forecasters as the next storm gathered strength offshore. In a region where every minute counts, the reliability of this network shapes not just forecasts, but the fate of millions. At 3:40 in the afternoon, the fierce crackle of the municipal loudspeakers echoed through Dinalongan's narrow streets. Mayor Joel Batong stood shoulder to shoulder with his disaster council, his voice steady, but his eyes betraying the pressure. The latest PAGASA bulletin had just upgraded the alert to signal number 4. With winds already tearing at roofs along the coast, there was no time to debate. Within minutes, police and Bering officials fanned out, knocking on doors and urging families to leave everything behind. Some clung to their homes, unwilling to abandon animals or precious belongings. The mayor's order was clear. If persuasion failed, forced removal would follow. He told his team, no rescue once the winds begin. Repeating the line that had become a grim refrain. 6 hours before landfall, evacuation centers filled with the sound of crying children and hurried prayers. Field teams relayed updates over handheld radios. Voices sometimes lost in static as the first gust snapped power lines. Generators hummed to life in the municipal hall, the only place with steady light. Bong's phone rang non-stop with calls from regional officials, desperate parents, and his own wife asking if he was safe. With the main radio tower threatened by flying debris, backup frequencies were activated, and runners were sent between checkpoints with written orders. When the first reports of flooding came from the river barangays, the mayor faced an impossible choice. Send teams out into the teeth of the storm, or wait, and risk losing track of those left behind. He chose caution, locking down the coastal perimeter and halting all travel. Later, as news of 2 deaths filtered in, one a drowning and the other a roof collapse, Bartong's frustration was raw. He said they had done everything humanly possible, that their town was evacuated before the typhoon arrived, but nature's force was beyond prediction. The unfortunate deaths happened when townsfolk tried to go back for their things, not realizing the surge would hit so fast. In the end, every minute counted and every decision weighed on his conscience. 90 minutes after midnight, a desperate voice crackled through the static. Fishermen aboard the San Lorenzo, 3 kilometers off Casaguaran, were losing power fast. Their engine was dead. The auxiliary generator, already drowned by the rising sea and waves, were now cresting over 8M. The crew's radio plea came in broken bursts. We're adrift. Hull taking water. Anyone please. The Philippine Coast Guard cutter Bagong Bayani was already fighting its own battle. The blackout had swallowed the coastline, and only the faint pulse of emergency beacons cut through the rain. Every navigation system flickered between error codes. Still, the captain pressed on, steering by memory and instinct as wind gusts slammed the vessel broadside. The deck pitched violently, sending equipment skidding and forcing the rescue crew to lash, revealing nothing but chaos. The crew relied on handheld radios, voices trembling as they tried to triangulate the San Lorenzo's last known position. A rescue rope was fired across the gap, but it snapped in an instant, lost to the churning dock. On the open channel, a Coast Guard officer's voice broke through. I can't see the hull. God help us. We're drifting. For an hour and a half, the Bagong Bayani circled blind, engine straining against the current, every minute stretching the line between hope and disaster. Lightning-lit faces in a fisherman's cell phone video, hands white-knuckled on the rails as the cutter finally loomed out of the storm. The crew hauled the survivors one by one over the side, shivering and silent as the wind screamed on. The rescue ended with all hands saved, but the sea had nearly claimed them. On shore, no one could explain how the cutter found its mark in that darkness. Only that the rules of survival, like the rules of the storm, had been rewritten that night. As dawn broke over Luzon, the world's most advanced satellites locked onto Typhoon Fung Wong. From space, the storm looked almost unreal. A perfect spiral with the eye wall unbroken, and a cloud shield stretching so wide that meteorologists at the Joint Typhoon Warning Center started to question their own models. Himari 9's infrared scans suggested a storm diameter approaching 1,400 kilometers, while Pegasus' Doppler radar, when it was online, tracked bands that seemed to reach from the Pacific coastline all the way to the western plains. But as the data poured in, the numbers refused to settle. Some satellite wind field estimates hinted at a system far larger than anything in the books, while ground stations, where they survived the onslaught, reported wind speeds that fit more typical super typhoon profiles. Inside the forecasting rooms, a quiet debate turned fierce. Pegasus' lead analyst stuck to the A's protocols, insisting on a storm size just within the upper limits of known Pacific typhoons. Across the ocean, Joint Typhoon Warning Center forecasters circulated a leaked message stating that this defies the known physics of band formation. The phrase bounced through meteorological forums, fueling a rush of speculation. Was Fung Wong a single massive engine? Or was something stranger at play, a multi-vortex structure hidden beneath the swirling clouds? The science was not just academic. Wind field diameter determines who gets warned, who evacuates, and where resources are sent. Pagaza's conservative estimate meant some regions stayed on lower alert, while the Joint Typhoon Warning Sea Center's more aggressive modeling triggered warnings across an area almost the size of Western Europe. The clash between pixels and physics left emergency planners in limbo, forced to choose between conflicting projections as the storm bore down. In the end, every decision hinged not just on what the instruments saw, but on how much uncertainty the scientists were willing to risk. In the hours after landfall, coastal engineers began the grim task of measuring what the models had missed. In Bela, Aurora, tide gauges and port cameras recorded water climbing to 3, 5 m, sometimes even 4 m, swamping the river mouth and pushing more than 200 m inland. That surge, nearly 1 meter higher than official forecasts, left entire Bangis underwater long after the winds had eased in Burak Katandus and Pandon Cameron's north. The story was the same. Watermarks on school walls and market stalls showed run-up levels that defied the guidance local leaders had relied on. In Virak, peak surge reached 3, 5 m, flooding the port and sweeping debris deep into town. While in Pandon, the sea pushed farther inland than any living resident could recall. Engineers tracing the disaster point to the way Fung Wong's massive wind field and the unique shape of local bays combined to focus the surge. In Bela Bay, the coastline bends into a natural funnel, amplifying the force of water driven by hours of unbroken onshore wind. At the same time, torrential rain from the mountains poured down swollen rivers, meeting the rising sea at exactly the wrong moment, high tide. The result was a compound flood, overwhelming defenses designed for smaller, slower surges. In some places, the water continued to rise even after the storm's eye had passed, catching families who thought the danger had ended. Post-storm surveys confirmed the models had underestimated not just the height of the surge, but how far it would spread. Engineers found that outdated maps and incomplete data on river mouths and sandbars had left blind spots in the forecasts. In Bela, the difference between predicted and observed surge meant hundreds more homes flooded. In Varak, emergency plans based on lower numbers fell short. For coastal scientists and engineers, these failures are more than academic. They are a call for urgent fixes, better data, and models that can keep up with storms that refuse to follow the rules. In the chaos of Fung Wong's landfall, the country's warning system cracked open. As the storm battered Aurora and Ball, the BOR Doppler radar, crucial for tracking rainfall and wind direction, went dark for nearly 18 hours. For coastal tide gauges, including those in Bela, Casiguran, Apari, and Infanta, dropped offline just as the water began its deadly climb. 3 weather stations in eastern Luzon lost full data feeds for over half a day, leaving meteorologists with only scattered readings as communities faced the surge. In hard-hit Barron, the absence of live sensor data meant flood warnings lagged by an hour or more. Emergency managers later admitted that situational awareness was severely degraded at the worst possible moment. Relief logistics faced their own ordeal. The Department of Social Welfare and Development had prepositioned a record 2.04 million family food boxes across Luzon and the Visayas. But as evacuation numbers soared past projections, local hubs in Aurora and Isabela found their stocks running thin. Blocked roads and closed ports left entire towns waiting, sometimes for days, as supplies sat out of reach in regional warehouses. Humanitarian trackers flagged the gap. Record stockpiles on paper, but distribution paralyzed by impassable routes and missing real-time data on which communities were cut off. Mighty Yanel Tan, a leading climate activist, voiced the frustration of many. She said, "People keep hearing about investments in disaster response, but the sensors are old, the networks are fragile, and last-mile delivery breaks down when it matters most." She warned that the government needs to treat science and adaptation as survival, not an afterthought. For millions, the storm exposed how quickly even the best-laid plans can unravel when key links in the warning chain fail. 5 signals now stand out, each one pointing to a storm era that refuses to obey old limits. First, the Western Pacific Sea surface temperature anomaly reached +1.2 degrees Celsius this season, enough extra heat to supercharge any cyclone that forms. Ocean heat content east of Luzon was also at record highs, giving Fung Wong a vast reservoir of energy even as it crossed land. The Madden-Julian Oscillation, a global pulse of tropical thunderstorm activity, arrived in phase with the storm's birth, stacking the odds for rapid intensification. Atmospheric moisture was off the charts with a persistent trough, drawing deep water vapor across the West Pacific. At the same time, vertical wind shear, normally a typhoon's enemy, remained unusually weak, allowing Fung Wong to keep its symmetry and strength when most storms would unravel. Each of these factors alone is a red flag. Together, they create a recipe for extremes that cannot be explained by luck or chance. Dr. Ronald Villerin, an atmospheric scientist, put it plainly, this is not just a one-off event. The storm structure and energy profile suggest we are entering an era when the bounds of cyclone behavior are shifting. For scientists, these signals are not just warnings. They are evidence. The future is no longer about the storms we remember. It is about monsters we have yet to imagine. Today, as evacuation centers fill and meteorologists scramble for answers, the Philippines faces storms that defy prediction and preparation. Fung Wong's unprecedented power exposes how climate extremes now outpace our models and our response. The warning is clear. Nature's new playbook is already being written. Are we ready to read and act before the next page turns? Santorini's hidden fault lines are moving. Is it the next big eruption? That's the question keeping scientists awake at night. Beneath the iconic whitewash cliffs, seismic alarms are registering tremors that echo the run-up to the cataclysm that vanished ancient cities and sent tsunamis racing across the Mediterranean. Right now, the very crust under Santorini is flexing as magma surges deep below, hinting at forces powerful enough to reshape continents. If you think the danger here ended with the myths of Atlantis, the truth is even more unsettling. Because what's stirring beneath Santorini could threaten not just Greece, but the world. So, what makes this island so explosively different? And how much time do we really have before history repeats itself? Deep beneath Santorini's postcard-perfect cliffs, a slow collision is unfolding on a scale almost impossible to imagine. The African tectonic plate, dense and ancient, is pushing northward, sliding under the lighter ion plate in a process called subduction. This is not a gentle movement. The African plate plunges beneath the ion at an angle, dragging seawater and sediments down into the mantle. As these materials descend, they heat up and release water into the surrounding rock, changing its chemistry and lowering its melting point. The result is a wedge of mantle that begins to melt, producing magma that is far richer in water and gas than the magma found beneath most volcanoes. This volatile magma doesn't just sit quietly underground. It collects in chambers and reservoirs, sometimes just 3 to 5 kilometers below the surface. The presence of so much dissolved water and carbon dioxide inside the magma is what gives Santorini its reputation for violence. When pressure builds, these gases can flash to steam in an instant, turning a slow, creeping flow of molten rock into an explosive eruption that can tear apart the crust above. The exact geometry of this underground system is mapped by seismic waves and satellite measurements. Studies have revealed that Santorini's magma plumbing is not a simple vertical pipe. Instead, it's a tangled network of sills, dikes, and chambers, some shallow and some as deep as 13 kilometers. The main shallow reservoir sits directly beneath the caldera. But deeper down, a broad pool of partially molten rock connects Santorini to the nearby Colombo volcano. This mid-crustal zone acts as a kind of magma highway, channeling molten rock laterally as well as vertically. The angle at which the African plate dives beneath the ion is steep enough to generate intense friction and heat, but not so steep that it cuts off the supply of water-rich sediments. This balance creates a perfect storm for producing magma loaded with volatiles. Every pulse of magma that rises through the crust carries with it a fresh dose of gas and heat, priming the system for instability. At the surface, the evidence of this deep engine is everywhere. The ring-shaped caldera, the black sand beaches, even the hot springs bubbling in the sea, all are products of this relentless geologic process. But the real story is unfolding out of sight, where the plates grind, water seeps, and magma accumulates under growing pressure. Here in the darkness miles below Santorini, the countdown to the next eruption begins. Not with a bang, but with the silent, unstoppable movement of the Earth itself. Santorini's caldera isn't just a scenic marvel. It's a wound in the Earth that refuses to fully heal. The cliffs that ring the island are the jagged rim of a collapsed volcano. Their layers stacked with ash, pumice, and shattered rock from eruptions that tore the island apart. These scars are more than ancient history. They are the surface expression of fractures that run deep into the crust, forming a lattice-work of faults that slice through the caldera and the seafloor beyond. Some of these faults trend southwest to northeast, perfectly aligned with the direction of the most recent seismic unrest and the hidden magma corridors revealed by modern imaging. Unlike the gentle lava flows of Hawaii, Santorini's eruptions are sudden and violent, driven by magma rich in gas and water. When pressure becomes too great, the magma doesn't always take the most direct route upward. Instead, it exploits weaknesses. Old caldera walls, buried cracks, and the very faults that define the island's shape. These structures act as escape valves, guiding magma sideways as well as upward, sometimes bypassing the main volcanic center altogether.